All right. Good morning. Welcome to our second day. I know you've been listening to some wonderful talks this morning. As sort of a reminder or notification, really, I'm going to put this back on the stand because this is recorded. If we get to questions and you want to ask questions, please just come up to the microphone. That way, anyone who's on Zoom can hear it as well. All right. So to finish out this year's POMU Epsilon conference, Ben Orlin will be talking about the entirety of higher mathematics in 9 puzzles. So thank you.
Thanks everybody for having me here. Yeah, congratulations. The student talks were all wonderful, I thought. They're really cool. So in a way, the nice thing is you guys have already covered probably 80% of higher mathematics. So it's really just the last little bit that I need to cover in my talk, which I appreciate you guys taking so much off the table for me. Yeah, let's see. So I did that games book a few years ago, and this I'm sort of winding up. I think the next book I'm going to do is going to be a book of puzzles. And yeah, puzzles I like. I don't know what it is, again, what it is that attracts me to puzzles, but there's something about taking the whole weird, maddeningly complex reality that we live in and distilling it down to, like, here are the 3 assumptions, here are the 2 choice variables that you have, can you solve it, can you do it? There's something really gratifying about that process. And I'm not the only one who feels that way, I think, because that's math. That's what's always drawn people to math, is taking this really complex world, boiling it down to some simpler logical system, and then being able to deliver a solution or a proof that there is no solution or something like that. So anyway, I've got my image. There we go. There's my books again. It's fun. They're pretty big books already, but it's fun being on this stage and seeing them at, like, larger than the St. John's Bible, really big. So anyway, all right, puzzle number 1, ready? And you should turn to the person next to you and be like, all right, ready to do puzzles together? Give them a little nod, give them a little, what's up? Fist bump if that's what you like to do. Okay, here's your first puzzle, okay? Your friend gets into town. Let's see, slide, there we go. Your friend arrives early in the morning, early morning flight, May 19th, leaves at the end of May 31st. When your friend's in town, you get lunch together. How many lunches do you get together? Talk about it with your neighbor. Turn and say, hello, good. You are someone I'd love to get lunch with, and how many lunches are these people going to get together? Mm-hmm. Let's assume these are, they eat lunch like a normal, these aren't like midnight lunch people. Yeah. It's not, yeah. Not hobbits, human beings. As you can tell from the diagram, they look like true human beings, right? Do we have an answer? What's our answer? This one, we have other puzzles that are a little more involved than this one. I won't belabor the answer here. Did we all get 12? Okay, good, because 12 is not right. I've thrown this at people. Now, you guys were prepared. Your minds have been sharpened by 2 days of talks. This one, it's somehow really hard for people to avoid saying 12. Because 19 to 31, like 19 minus 31 is 12, but it is 13. Which is weird. I saw some folks out there counting on their fingers. That is just the right way to do this. That is the advanced technique that you need to handle this problem. Okay, so what does this have to do with higher mathematics? It was quick. I wanted to throw it at the beginning so I could up my puzzle count a little bit in the talk. And also, oh man, it's funny. I'm used to seeing my drawings. They look pretty bad at 8.5 by 11 size, but then you zoom them up to like epic movie scale, IMAX version. Anyway, this is, what do I like about this problem? Like, it feels like it should just be 31 minus 19. It feels like that should be the calculation you need to do, but we think about days and time weirdly, actually. The way we count time is odd. So if somebody arrives at the 2nd and leaves on the 4th, they've been in town 3 days, 2, 3, 4. You just get these off by 1 errors because of the kind of quirky ways we talk about time. You see this with kids' ages too, right? Like, you are 5 years old until the day that you turn 6. Even though you're like 5.99 at that point, right? It's a little weird to call that 5. But we truncate and round in weird ways with time. So you've got, in math and in puzzles, what happens is you've got the abstract logical structures that we like to study as mathematicians, and they run into the weird world of reality. and all these thorny little ins and outs and exceptions that we've built for ourselves in this human world and that just exist in the natural world. And so that, that braiding together of the pure and the applied, the abstraction and the application. Anyway, that's kind of the essence of mathematics as a discipline, I think. Okay, and often consequential. This is an old cartoon I drew back when this felt like the most recent financial crisis. So quite a few financial crises ago. But Lehman Brothers, yeah, right. That was a firm that lived for a while, and then they said, you know what? Houses are probably independent events, like someone defaulting on a mortgage. There's no connection really among these things. They're a very low level of dependence. We'll model them essentially as independent events. And that was the end of the company. And not to mention the world economy. All right, puzzle number 2, this one a little more involved here. Another counting puzzle. Graduation parties. So, right, we got some seniors in the room. We have seniors? Yes? Okay, cool. Yeah, wonderful. Well, you can look forward to a graduation party like this. This one has 100 graduates. You can do this with any number. And everybody gets a checklist of the other 99. So everybody else attending the party. And what you do is you take photos together, all kinds of photos. So like 2 people take a photo together, 5 people take a photo together, whatever. After you're in a photo with someone, you just check their name off the list. And so at one point during this party, someone stands up and is like, oh, it's a party of mathematicians, I think. Look, everyone's list has a different number of check marks. And everybody groans and goes, that is ridiculous. Of course they don't. So why is that impossible? Can we prove that this cannot happen, that the person who says everybody's got a different number of check marks right now necessarily is lying? And I'll come back to this slide in a second, but to show you, you do not want to brute force this one. Exhaustive search is not going to get you there because, right, two graduates can take up to 4 photos, right? There's both of them, the selfie, the other person's selfie, or the not very interesting empty photo, the null photo. 100 graduates, we've got something like 2 to the 100, we're at that order of magnitude possible photos. You probably don't want to start imagining all the possible sets of photographs that could have been taken. So going back here, talk with your neighbor for a minute, see if you can come up with a convincing argument for why this is impossible. All right. I feel like that seems like the sound of consensus slowly being reached. Does anyone have an argument that they like, that they would want to share? Yeah.
Yeah, 100 numbers from 0 to 99.
Sure, right. So in theory, we've got just enough.
But if you have someone 99, then you're with everyone, but someone at 0 is impossible.
Yeah. So we've got the pigeonhole argument. You sort of want it to be just a pigeonhole principle argument right away. You can't quite do it at the first step, right? So because 0 to 99 actually does give you 100 possibilities. So it could be somebody's got 0, somebody's got 1, somebody's got 2, and so on, all the way up to somebody who has 99. But as you said, those can't quite happen all at once, because if there's somebody with 0, that means they've not been in any photographs. But somebody else has 99, which means they've been photographed with everybody. And so you could have, right, this argument doesn't rule out having 0 through 98 or 1 through 99, but it does rule out having 0 through 99. And so then you have not quite enough numbers for all 100 people to have a different one, and so the pigeonhole principle argument goes through. There must be a repeated number somewhere in there. Anyway, that's combinatorics. So there we go. We're now partway through the discipline of mathematics. Yeah?
You could also argue that because the total number of check marks has to be the sum from 0 to 99, that's going to be an odd number, which means that, because every check mark corresponds to 2 people appearing in a photo together, they always have to appear in pairs.
Yeah, let's see. The 99, sum to 0 to 99 is, yeah, I think is even. Yeah, I think so. You're right. You're right to bring up the parity issue, because there's interesting puzzles you can ask. You can ask things, right, sort of related. There's puzzles like, could an odd number of people at any moment have an odd number of check marks? Which you got to be at a very specific kind of party to get people excited about these questions. Like, this might be just the right room to make this happen. I think if you bring in your English majors and your history majors, they're going to be a little bit like, I'm not really that worried if there's an odd number of people with an odd number of check marks. But yeah, the parity arguments, you're exactly right. That's an important observation, that that the check marks come in pairs. You can imagine instead of an undirected graph version, or yeah, right, it's a bidirected graph version of this problem. You could imagine a directed graph version where you're allowed to sneak up and surreptitiously take a selfie with someone behind you. So it's like, I take a picture with you guys, but you didn't see that I took the picture. So I check you off, but you don't check me off. And then that would change the combinatorics. But as you can already sort of tell here, and this is something I like telling to people who are sort of outside of the mathematical world, that one of the trickiest branches of mathematics is counting. It's really counting is really tough. Oh, it's just hard to get a handle on these. There are some theorems, but it's very hard to come up with big general principles for counting. It's just a very tough task in mathematics. And it's been interesting. I mean, like I'm not a historian of mathematics, but learning a little bit about sort of the changing role of combinatorics in mathematics throughout the 20th century. I think today combinatorics is like a cool branch of mathematics in good standing. Talking to people who worked on combinatorics in more like the mid to late 20th century, I think it had a little bit of a chip on its shoulder because it was a little bit left out. So it's sort of like, it's just counting arguments. It's not real math. And yeah, these things change over time. And combinatorics is now, I think, understood to be quite deep and interesting and rich mathematics. And in particular, I think maybe in the background, one of the driving factors of that has been the rise of computing. And like to be alive in the 21st century, and especially to try to do anything on a computer, as all our student researchers know, is to reckon with the combinatorial explosion. It doesn't take that many people to suddenly have an absolutely staggering number of connections among them, right? 100 people at a party, you are way beyond what you can brute force, right? The number of subsets of people is unfathomable. Even just the number of directed arcs there is quite a lot. And so I think there's something there where like the world around us changed and became much more combinatorially intense. And mathematics, to its credit, responded to the world around it. An unusual move for the mathematical community, but we do that sometimes. We look out and we change our ways. All right, this one is another puzzle, the 101 urns. Something I love about our mathematical community, it's always urns. It's not bowls, it's not baskets. Anyway, but here we go. We've got urns with 100 marbles each. We'll number them 0 through 100. So the first one, the number is just how many red marbles it has. So the first one has no red marbles and all green. And then the next one has 1 red marble and 99 green, and then so on, up until right somewhere in the middle, there's one that's 50-50, and then the final urn, we're up to all red. Okay, so these are the 101 urns, and we have them somewhere backstage. Is there? Okay, maybe backstage that way. I think it would be hard to hide the urns over there. That looks like the edge of the building. We pick a random urn. We go into the dark room. I send my assistant out there. They come back with an urn, jealously covering the top so no one can see what urn it is. A random marble is chosen. It's red. And that marble is then cast into the crowd. Someone gets to take it home. It is not put back in the urn. And we're going to take another marble from that same urn. Okay, so that urn now only has 99 marbles in it. And the question is, if you had to bet at even odds, would you bet on red? Would you bet on green? Or does it not matter? It's equally likely. So here's puzzle number 3. I will let you. After you finish this, you're 1/3 of the way through higher mathematics. So good work. Talk about this one with your neighbors, see if you can come to a consensus. All right. Seems like some groups have reached their consensus, others still chatting. But let's start with a poll. Let's see who thinks what here. So raise your hand if you think the marble is more likely to be red. Okay, that's solid contingent. Raise your hand more likely to be green. Okay, also some support. And what about equally likely? Okay, so we got support for all 3 in the room. This is, I think our number is slightly different than when this was done in a large online version. It's almost cut off at the bottom. You can see almost 23,000 votes in this poll. And this is Daniel Litt, who's, back in the days when I used Twitter. Daniel, I think he's at Toronto, I want to say. But it does lots of fun probability problems like this on his Twitter account back in the day. So this one got 23,000 votes. And it looks like, I think our majority was red. Daniel Litt's followers were mostly going green. Anyone want to give an argument for one or the other of these? We could start with, do you want?
I had an argument for green. I ended up not choosing green because he convinced me that it was 50-50.
Okay, all right. Well, let's hear the argument for green first then.
My argument for green was I think that it's very likely that the initial chance of drawing a red marble is 50-50 if you look like overall.
Sure.
So therefore, after you remove one red marble, it's now like 50.01 to 49.99. So it's technically slightly skewed in green.
Sure, yeah. So this is what I think of as like the effect argument, right? What was the effect? We're drawing without replacement. So we pulled a red marble and we threw it away. So in the whole world of marbles, there's a lot of marbles out there, but there is one less red, whereas at beginning, right, by construction, there were equal numbers of red and green. For the people who voted green, was that sort of what that was the logic? Yeah, yeah, so that sort of, I call that the effect argument. What about for red? Does anyone want to give an argument for red? Yeah. Yes, yeah, yes.
Okay, so if you think we chose an urn at random, right, but then we did pull a red out, which means it couldn't have been urn 0, because that one only has green in it.
Okay, yeah, this is a good point. So we've ruled out it wasn't the first. It wasn't that urn number 0.
That takes out 100 green from our pool. So we did remove 1 red, but we also removed 100 green.
Ah, yeah.
I think it's kind of more likely that we're going to get it out of it.
Ah, that's nice. Yeah, I've never heard someone actually give that argument sort of focusing so specifically on urn 0, but you're right, urn 0 is totally ruled out. Yeah, we can, my guess is there are others in the room who will want to extend that reasoning to something else. Yeah, yeah, go ahead, yeah.
The space that we're now dealing with is 99 urns, each containing 99 balls.
Right, sort of.
Number from 0 to 99, right?
Yeah.
Because we pulled 1 red, 1 out, and it's going to be one of those. So I was going to say that it was even, but I do think that it's more likely to be red because the fact that we pulled a red one out of it in the first place does make it more likely. It does weight the probabilities towards the end that we have it burned with more red balls in it.
Yeah, yeah, I think of that as the extension of this argument. Right? You've really taken that extreme case and said, okay, it's definitely not the one that was all green. But similarly, all right, and so that was my last little animation of we eliminated that red one. I call this the information argument. This is sort of the other side. So one piece of information we got was it's definitely not the all green urn. But also, it's probably not the 99 green urn either. Right? Like maybe we picked the one that was 99 greens and 1 red, and 1 in 100 chance we just pulled out that red. Pretty unlikely, though. Or maybe it was the 95 greens and the 5 reds. But again, you wouldn't expect to pull out a red. The fact that we pulled out a red tells us something. Because there's some urns in here that are really heavily red and some that are really heavily green. If the first one you pull out is a red, probably the one you pulled from was a pretty red urn. And so in this case, the information does overwhelm the effect. I suppose the argument for even might have been that these effects kind of cancel each other out perfectly, right? That like the information you've gained is balanced by the fact you threw away a red. It is not balanced. It is, in fact, the odds are pretty dramatically in favor of it being red. So I can give you a very quick, I wonder, I should have included the slide where I show the argument for this. But we'll do a very simplified version with just 3 urns. So imagine we've got just 3. Construction is the same. And then we pull out a red marble. So each of these 6 was equally likely to be chosen originally, right? And so when we pull out that red marble, it could be any of the 6 except for, well, it's not one of the greens. So we know we've got one of those 3 red marbles. And each of them has an equal chance of having been chosen, any of those reds, right? We have no way. These red marbles are all identical, so we know it's one of those 3, right? If it was that one, then the next one will be green. But if it was either of these from the 3rd urn, then the next one will be red. So 2/3 chance that, yeah, it is, I'm not sure if it's isomorphic to Monty Hall, but yes, it certainly is very similar to Monty Hall. So if you see a red, right, there's a 2/3 chance you picked it from that 3rd urn. And thus a 2/3 chance the next marble is red. Interestingly, do you guys want to hear the argument for 100 urns? I think I can do this briefly for you, even though I didn't include the slide on it. The probability is 2/3 for any n, which is sort of shocking. But here's what you do. You imagine, we've already numbered the urns, right? So, right, like urn number 37 was, I'm not going to remember which one's green and which one's red. I think urn number 37 was, 37 has 37 reds in it, right? Okay. So what we do is we then number the marbles in each urn. Okay. So if you're below the urn number, that's red. and any numbers above the earned number are green. Okay, and now what we're doing is we're picking 3 numbers from 0 to 100. By construction, they will all be distinct. Right, so we're just getting kind of 3 numbers, and it's essentially a uniform distribution subject to that all distinct qualification. And so there's 6 orders that 3 numbers can happen in. Right, we've picked earned number, there's the number of marble 1, and there's the number of marble 2. And so since basically you can write down the orders, I'll let you guys do, you guys got the paper, I just have gesticulating hands up here. But you write down the 6 possible orders, right? It can be, you know, marble 1 is the smallest, then marble 2, then the earned number, or the earned number could be the smallest. Anyway, there's 6 possible orders, and you will find very similar to this that 3 of them we've eliminated because they would have resulted in a green marble first. And then so that gives 3 remaining orders, and 2 of the 3 give you both red marbles, which is essentially just a generalization of this argument. Cool, good, that's fun. I like, yeah, I'll be honest, usually I don't talk to groups where I can give an argument without a slide, and it's like, oh yeah, I'm following along, cool. So it's great. Anyway, this is of course probability. We're now on to our, this is what our second branch of higher mathematics, the mathematics of uncertainty. And the thing I like about probability is that we are often uncertain in life. I am uncertain about things ranging from how to solve a math problem to like, what day is it? Really a wide range of things I'm quite uncertain about. And probability is what gives us that. The language I like to use for this, and sort of the philosophy of it, I guess, is that we think of history, writ large, like everything that happens in the world, as having some element of randomness in it, right? It's like it's been dealt from a deck of cards. And then what probability does is this kind of weird imaginative move. We grant ourselves access to the deck. We imagine we know the deck of possibilities. And we call it a distribution, which makes it sound really quite dry and dusty. But a distribution is much more. A distribution is like omniscience. A distribution is imagining you know all the possibilities and how likely they are. And then you look at the world and go, oh yeah, it's just a sample from the distribution. And it's kind of a funny way to think. It's not natural for a lot of people to look out at this kind of chaos and be like, it just happened that way. There was this world of possible things that could have happened, and this is just the world we got. But it gives you a lot of insight into understanding outcomes. It makes you a better predictor and a better contextualizer of things that happen in the world. OK, number 4, ready? Basketball time. Yeah, I enjoy following basketball. Basketball fans in the audience, a little bit? OK. 2, all right, 1.5, all right, good. That's fine, that's fine. You don't need basketball knowledge for this one. Okay, so let's say we want to know, this is something I find interesting to do, look at people with these really exciting, high-profile careers, right, basketball or music stars. And you say, like, how long does that last? How long does that flame burn? So I want to know the average length of an NBA career. But I'm lazy. So what I'm going to do is I'm not going to look at I'm not going to download some CSV with all the NBA careers ever. Some of them are still going on anyway. I'm just going to pick a random year, say 95. I'm going to pick a random team, let's say the Supersonics. And instead of looking at all NBA players in history, I'm just going to look at the 15 guys who played on the Supersonics in 1995. That will be my sample. I'll calculate their average. I'm going to even specify in advance, don't worry about the specific team or the specific year. Let's assume, roughly speaking, a typical team in a typical year. And the question is, when I calculate their average career length, right, looking at those 15 guys on this team, on average, should I expect to get a number that's actually too high, too low, or on average about right for the length of all NBA careers ever? So that's the question. Take a minute to talk about that with your colleagues. All right, let's take a poll. Yeah, so let's, again, as we did with the urns, let's take some votes. So who expects this to be too high? This is going to be too high, this number. Who thinks too low? Could be, OK. And who thinks should be about right? OK, all right, nice. Again, we have support for all 3. Anyone want to make an argument in defense of their take here? Let's see, yeah, we could get any. Yeah, go for it, yeah.
You're more likely to choose people who have longer careers, so it's more likely you have a chance for them to appear in the sample.
Yeah, is that for those who said longer than average? Was that your thought? Yeah, yeah. This problem came to me because I teach an intro stats class, and one of the projects we do is like go come up with a question you want to know about, pick a big population that you couldn't sample that whole population, and then go find a sample. And the first year I did it, one student was curious. He was like a guy who likes going to the gym, and so he was like, okay, I want to know, on average, how often do people go to the gym? So I'll go to the gym, and I'll ask people, how often, on average, do you go to the gym? And yeah, right, so I was like, that is, I see why you're thinking that is a sensible way to do it. And there is an adjustment you can make. We can do this in this spreadsheet to make the adjustment. But what you're going to do is you're going to show up at the gym, and you're going to be like, wow, people go to the gym a lot. Because if your gym is, 10 people who go every day, and 100 people who go once every 100 days, you're going to show up at the gym, and you're going to be like, wow, there's 11 people here. 10 of them are here a lot. They say they come every day. And then there's this one random person who comes one every 100 days. You're missing the other 99 of those people. And all the people with gym memberships who never come, you're certainly not going to get them in your sample. So yeah, it's the same issue here as you're saying. This is the actual, I did it with the Supersonics. And actually, part of it is what I said was a lie. The Supersonics were actually a really good team that year. And so they had more good players, and good players have long careers. But take a bad team, the Celtics from a year or two later, and it's still, that's too long. Average NBA player does not last 10 years in the league, right? If you actually take the entire population, it's more like 3. So why are we getting such high numbers? It's exactly this issue, and it's quite a dramatic effect in something like the NBA. What we really want is we want sort of the bag of all NBA players. We would like to put all of them in a bag. And I think it's the first time these slides have ever been projected, where those are now the size of actual NBA players. So that's what we want to do. We want to reach into that bag with all the NBA players there. We want LeBron's name is in there, and Michael's name is in there, but everybody's name is in there. Everybody who's ever played a minute in the league. But this isn't what we reached into. What we did is we effectively reached into a bag of NBA rosters, right? They were organized into like sub-bags, one per year, but effectively it was like a bag of rosters. And so, the 1999 Pistons are in there, and the 2000 Pistons are in there, and so on and so on and so on. And if you had a short career, if you played 1 year in the NBA, because you're only 10,000 times better at basketball than I am, and not 100,000 times better, then you'll be on one roster. But if you're LeBron, and you've been in the league since, I don't know, time immemorial, no one in this room was alive when LeBron started playing professional basketball, you're going to be on a lot of rosters. And so you're very likely to wind up with a roster that says LeBron James on it, and very unlikely to wind up with a roster that says LeBron James Jr. on it. No, he's only played one. He could have a long career. My guess is he will not play 20 years in the NBA. So we're oversampling players with longer careers, and indeed the sample will be too high. As our 2 samples showed, it was dramatically too high. So this is statistics, which I'm calling a branch of higher mathematics, although really statistics is essentially its own discipline, I would say, with its own traditions and set of questions, although certainly growing out of mathematical concerns. And the way I like to talk about statistics is it's reasoning from limited data, right? It's drawing inferences from what little we've seen of the world. And so essentially it's an inverse problem. Probability is saying, let's imagine we've got the deck, we've got the distribution, what stuff could happen? And statistics is saying, well, we just saw a lot of stuff happen. What was the deck, right? What was the distribution? And that is inherently a hard problem. My intro stats students find this very unsatisfying because we never are certain in statistics, right? You can't have a 100% confidence interval because that would be 0 to infinity, right? Like you just never know a number precisely in statistics. It's always with some level of confidence. There's always a chance that random error has completely thrown everything off. So that's statistics. Good. We're like almost halfway through higher mathematics and about halfway through the talk. So good. We're setting good pace. Puzzle number 5, the dodgeball standoff. Here we go. You are. Oh, wait, it's not you. 3 players are in a dodgeball tournament, but you're player A. Okay. They take turns throwing. This is a weird dodgeball tournament. Usual dodgeball is chaos. Some tyrannical gym coach has been like, no, we're doing this structured, okay? So everybody takes turns throwing. You're allowed to try to dodge when they throw at you. If they hit you, you're out. 3 players left. Everybody else has been knocked out. Player A is going to go first. This is you. You're a 30% shot. Don't know how you made it this far, honestly. You must be pretty good at dodging. Player B is a 90% shot. They're good. You can see why they're here. And player C, they call them the annihilator. 100% shot. They don't miss. They don't miss. They take aim. You're out. So player A is going to go first, then player B, then player C, and it just repeats like that until everyone's gone, right? Who should A aim for? This one, I don't think will take tons of discussion, but talk about that with your neighbor. All right, let's poll it. Let's poll it. So you're in player A's shoes. Who would like to aim for player B? One or two. OK. Who would like to aim for player C? Almost everybody. Raise your hand if you didn't vote. OK. Why not?
Because you're supposed to aim for nobody.
Yeah. So one thing you could do as player A is just be like, I give up and just aim for yourself. But a better option, indeed. Yeah, is to, right? Yeah, that's a good point, right? Trying to take myself out of the game, but maybe that's what player has been doing all along, was trying and missing every turn. So we can go through the possibilities, right? A few people were thinking maybe we should go for B. That's fine, except for it's not actually, because if you hit B, then B is out, so B doesn't take a turn. Now it's C's turn, and the Annihilator is going for you. That's bad news. You don't want that. So we're not going to do that. So go for the Annihilator, right? We had a few votes for that. Let's aim for C. Now, maybe you get lucky and you hit C. It's only a 30% chance, but OK, maybe you take them out. Whose turn next? B's turn. And they've got a 90% chance of hitting you. So 90%, you're eliminated right away. Maybe 10% chance you're lucky and they miss, in which case you'll probably still miss them, and then they'll beat you the next time. So you wind up with like a 1 in 30 chance, right? If you sort of do an infinite sum of like maybe I get it on the second one, or maybe I get it on the fourth one, but like it's not great odds. But if you miss, which is, to be fair, what you're likely to do anyway, then B is going to go after C. Because B is not foolish. B is not going to be like, oh, I'll just leave C alone and take out A. No, B is going to go for C, and probably B takes out C. Or maybe B misses, 10% chance, in which case C is going to take out B. Either way, at the end of those two turns, one of them is gone, and it's your turn again. And so now you've got sort of a first mover advantage, right? If you actually took out B or C, you're no longer the next move. But if you just throw the ball away, let them take care of each other, now you have the next move. And so you've got at least a 30% chance, and indeed a little larger than a 30% chance of victory, which is not great. But also, you're not great at dodgeball. So it's, this seems like the best you can hope for. So this is, of course, the famous, right, the solution is to miss on purpose. This is the classic Truel problem. It's usually done with lethal weapons. I've changed it to dodgeball because I feel like that's gets the point across. And this is game theory, right? Which I think of, it's really hard to write a pithy definition of game theory. I think of it as the mathematics of strategic interactions. Right? So situations where you are making choices, an opponent is making choices, and your choices, it doesn't have to be an opponent, let's say another person is making choices, and those choices influence the outcomes you both experience. Another way to call it is the mathematics of conniving. So A's appropriate conniving here is to just throw the ball away. Again, I quoted this book last night. This is an actual quote from John von Neumann, who was the architect of game theory in the early days. And what he said about it, the legend has it, I don't know how true this is, but that he was inspired to create game theory because he just wanted to win his weekly poker night. Like his neighbors played poker, and he was like, I've got to beat these guys. And so hence game theory. But he said real life consists of bluffing, of little tactics of deception, of asking yourself, what is the other man going to think I mean to do? And that is what games are about in my theory. Right? Bluffing is very central, right? A sense of usually, not in the Truel problem, but in a lot of game theoretic situations, what you need is some element of randomness. To give away information about what you're doing is to give up one of your advantages in the game. All right, next problem. OK, this is a quick one. This one just happened in life. This is me and my brother and my 5-year-old were building trains, like little, you know these train tracks. And we built this formation. And then, so 2 trains are going to start here. OK? And this is a very simple puzzle. If they move roughly at the same speed, about where on the track will you expect them to collide head on? So take this is like a 1-minute conversation with your neighbor. Possibly a less than 1-minute conversation. I was tempted. Do you mind if I take a photo of you all doing? All right, appreciate it. Yeah. Oh, sorry, I couldn't hear. Could you say it again?
Are they being
Oh, let's assume they've got little imaginary motors that keep them going. Because if they acted on by gravity, they would kind of putter out pretty quickly. But let's imagine that we sort of like, we've got a hand moving them at a constant speed. Yeah, good question. So what do you guys think? Where are they going to collide? They're not. They're not. Because they go there, and then they go there, right? The blue one keeps going around. The yellow one's going around that way. And now you can see it already. The blue one is going to be chasing the yellow. And they'll be chasing each other forever. This like really caught me off guard, and I was just like staring at the train track for like 3 minutes. I was like, what did we do? Like, how did that? We weren't trying to do that. We weren't trying to build something that was sort of topologically interesting. But indeed, this is just the way it turned out. That middle track, you can only traverse once. So there's kind of that the track where they started, right here, right? That is traversable sort of precisely once, and then it gets you going. It sort of switches what direction you're going, I suppose. Is that right? Yeah, that's right. And you can only access it from going one direction. So they never collide head on, and in fact, they never return to that original position. So this is right. I used the word already. This is topology. And yeah, I love topology just as a branch of math. The fact that this is a thing you can do, right? Because it grows out of geometry and sort of geometric situations. Geometry is literally, right? Geo is Earth. Metry is measurement. So geometry is literally the measurement of the Earth, right? This is where its origins come from. It's finding how long things are, the area of things, the volumes of things, like measurements of angles. Geometry is fundamentally about measurement. And topology is like, what if you did geometry, but you didn't measure anything? It's like, well, then you wouldn't have anything, would you, right? Like, there'd be no, you're gonna let things change size, you're gonna let things change shape. But like here, right, the speed is a measurement, and it doesn't matter here. It doesn't matter what speed they're going. They don't collide. So, right, you can think of it as the study of invariance under continuous deformations, right? That is more traditionally how topology is described. But I think of it as like what's left when you throw out any notion of size or measurement in geometry. And the answer is a lot of interesting structure is left. So it's an old cartoon, right? Obviously, here in the real world, we tend to think of ourselves as pretty sensitive to measurements and geometries, right? Like if I buy the wrong size shoe, and I'm like, can I get this back for the right size shoe? And like, it's topologically equivalent to the shoe you want. It's not going to be a very satisfying experience. But, oh, and this is another cartoon. This is an old one. This before I have my own font now for my handwriting, but this was hand-drawn. Right. So if you're charging according to topology, right, they both have genus 1. So regular sized donut and mini donut are going to be the same price. And of course, a donut hole would be cheaper no matter what size it is. So that's fair. Anyway, right, obviously this isn't, topology is easy fodder for jokes. But also with weird connections all over the place, which I think we'll get to in a moment. Good, the perfectly satisfying doodle. This is puzzle number 7. Let's see how we're doing on time. Good. We're going to cover all of higher mathematics. No problem. So here are some doodles. Okay. Let's define a satisfying doodle as a figure that can be drawn without lifting your pen from the page or retracing any lines. You can do it in one motion. A perfectly satisfying doodle is satisfying no matter where you start on the image. And an unsatisfying doodle is one that is not satisfying, right? You can't draw it without picking up. You must pick up your pen or go over a line twice. So of these 9 figures, 1 is unsatisfying, 8 of them are satisfying, and 1 of those 8 is perfectly satisfying. So hopefully you have a pencil with you or just a neighbor who will let you fog up their glasses and trace out the shapes on their glasses or something. So see if you can figure out which one is which. All right, have we found the unsatisfying one? Yes, where's the unsatisfying? Bottom right, is that one unsatisfying? Top bottom? Yeah. Top middle? Is that, yeah, yes. This one is indeed unsatisfying. Has anyone found the perfectly satisfying doodle? Bottom middle is what I'm hearing. Do we agree with that? Have you tried drawing it from every point? Sounds slow, sounds tedious. So right, what we obviously want is something a little more general than that. My guess is this is a thought that will be familiar to some of you, but I like it, right? When your pen passes through a point, it always leaves 2 trails of ink, right? One as it arrives, one as it departs. And so we call this even degree, right? The number of trails coming out has to be even. You can come back through the same point again, and then you'll get another 2 trails, right? So for example, at the middle of an X, right, you pass through once, you pass through twice, you'll get 4 trails. You could even have 6 trails of ink coming out. But you can't have 1 trail, or 3 or 5 trails, unless that's where you started, or that's where you ended, right? Because the starting point, you didn't arrive there, you just transported in. So it only has 1 trail coming out, and similarly, your final point, you didn't leave, you just arrived and lifted out. So all we have to do is count each vertex for is it odd or even, for how many trails are coming out. So this is called degree in graph theory. And we can circle the odd degree corners. I've done it for you. And you'll notice of the 9 pictures here, 7 of them, right, all except for the 2 you identified, have exactly 2 odd degree corners. And so if you start at a different place, you'll get stuck. But if you start in one of the odd degree corners, so like this one down here, you start down there, you start drawing, maybe you do the box, you do that, and there you go, you're fine. You will always need to start in one of the yellow corners and end in another of the yellow corners. The one on top, it's all yellow corners, or it's 4 yellow corners. So it doesn't work, you can't do that. And the one on bottom has no yellow corners. So there's no necessary start or necessary end. You can do an Eulerian circuit from any point. So there you go. That's our bad one. That's our good one. Cool. Well done. And this, of course, is graph theory, which is, right, sort of all over the place. We've heard, all right, we had a great student talk about graph theory. I think of graph theory as one of the things you see as you get deeper into mathematics is like these very weird connections, right? Like, so graph theory, where does it begin? It sort of starts with counting situations sometimes and like simple networks of connection. And then topology starts with like geometry, but we threw out all the geometry. These don't sound like obvious friends, you know? And yet, depending on what your perspective is, graph theory is just an aspect of topology, right? It's just a topological subclass. And so you get sort of wonderful connections between different branches of math that don't seem on the surface when you're starting these puzzles related. Anyway, and then of course graph theory has a whole wonderful language you can repurpose to alienate your friends and neighbors. Oh, this is one I drew recently. You got the complete graph, right? We're familiar with this, K5. But then I don't know. I think I was falling asleep one night, and I was like, just the word graph was changing in my mind, and then that one was my favorite, the complete giraffe on 5 vertices. It's actually pretty hard to do a complete giraffe on 5 vertices. Would have been much easier to do a complete giraffe on like 30 vertices, but anyway. All right, puzzle number 8. Good, only 2 left. All right, this is Brigana's limit. This is what I was working on. My second book was about calculus, called Change is the Only Constant. And one of the chapters in here is this puzzle, because I was working on the book, and a friend of mine came over, two friends of mine, and Brianna's an English teacher, and not someone who like describes herself as a big fan of mathematics. But she'd learned this puzzle from a colleague and showed it to me and the others who were gathered there, and it just stumped us for a minute. So here we go. We've got a rectangle, or sorry, not a rectangle yet. We just got a little L shape. That's 3. That's 4. So the question here is, what's the dotted length? 7, good, okay, good. That's not the puzzle yet. Yeah, I was stumped for ages on this one. I couldn't figure it out. No, length 7, yeah. Okay, so, and yes, perplexed, I was not very perplexed at this point. And then Brianna said, okay, what if I change it a little staircase pattern? Now what's the dotted length? It's still 7 because the 2 verticals make 3 and the 2 horizontals make 4, okay. I'm still not that perplexed by this, but like, okay, well, where's she going with this? And then we do a bigger staircase. What's the length? Still 7, okay. And then we do a bigger staircase. Length is still 7. And then we do that. What's the length now? Yeah, now it's 5. I was writing a book about calculus and how it's like, oh yeah, in the limit, everything kind of comes out beautifully and you just pass through the limit and it's all great. That's not great. 7, 7, 7, 7, 7, 7, 7, 7, 5. Why don't you take a minute, see if you and your neighbor you've taken calculus in this room, see if you can figure out why is that happening? What's going wrong? All right. I'm curious, does anyone have a satisfying explanation? Yeah, go for it.
So basically, one of the things that's very important in calculus, this is from a 3 below and Brown video.
Okay, yeah, no, the best source.
Thing with using a square around a circle to do basically the same thing. Which is basically you need to be very explicit about what your error is at each point, because your calculus, limit is only actually valid if your error tends to 0.
Sure.
And in this case, as well as in the circle case, it does not tend to 0, and you can show it doesn't tend to 0, which is why the limit doesn't work out.
Yeah, do you guys find that a persuasive explanation? Yeah, I'm never sure. It sounds pretty good to me. In these situations, I never know, am I just hearing the phenomenon described again? And then it's like, oh yeah, that is a correct description of the phenomenon. But like, do I have a sense of why? Right? Like, why do I need the error to do that, or why isn't this error doing that? I think that explanation I think pretty much captures what's going on here. Sorry, that was my old slide. This is of course right. We're talking about calculus, but really to really tackle these questions of convergence, we're talking about analysis, which I like to describe as the study of the continuum. Right? It's the study of continuous processes, continuous behavior, sort of the companion to discrete math. And in this case, another way to think about analysis, other than calling them really fussy pedants who always have to figure out the details, my wife is an analyst, is that basically it's a series of increasingly elaborate footnotes to Zeno's paradox. Or you can also say pointwise convergence, oh yes, that and $3 will buy you a cup of coffee. The issue with this problem is you're getting pointwise convergence, which is one kind of convergence, but it's a trash kind of convergence. It's just not that useful, pointwise convergence. And like, what does that mean? Like, you kind of need to dive into analysis to think about what these different, and that's exactly what your error issue is getting at, right? Like, what is the thing we're measuring? How is it changing? And as iterations go by, what is it getting closer to, and in what way? So this is an example I stole from my wife, when she teaches real analysis. But I like this one. This is another case of pointwise convergence. So say we've just got a little triangular wave, and it's just going to move across the axis. So after 1 second, after 2 seconds, after 3 seconds, it's found between n and n plus 1 after n seconds. And so we say, OK, well, as time goes to infinity, what happens? Yeah, at any given point, it's at 0. So it converges to nothing. Right? Because say you want to look at the point a billion steps down. Well, for a while it's 0. Then for one brilliant moment, there's the wave. And then it's 0 for eternity. So any given point, that's true of a billion, that's true of a trillion, it's true of every point. So every single point converges to 0. But that seems weird. The wave didn't go away at any step. The wave was always there, and yet it vanishes. And the reason is because this is pointwise convergence, right? We're looking at every given point. But analysts don't love pointwise convergence because it gives you weird stuff like this. If you're looking at something more sensitive, like the area, right? The area vanished under this convergence. Pointwise convergence will do that to you. It'll change areas. It'll change those lengths. But something like uniform convergence will not have that problem. So another favorite case of pointwise convergence, and this was one of the driving events in the development of analysis, is we see non-differentiable points on functions. Right, you take something like absolute value of x, and there's this sharp corner. You say, okay, well, how many sharp corners can there be on a graph? And then Carl Weierstrass comes along. He says, okay, well, let's do this. Let's take a cosine, and then I'm going to stack on top of it more cosines, faster cosines, smaller cosines, little da-da-da-da-da. And then we'll do it again. And actually, even at this step, you can't really see I need to do an inset, so you can see how fast those things are going. Now, at any given step in this process, we're going to keep doing this, more and more faster, faster waves. At any given step in this process, it's a perfectly smooth curve. But in the limit, it's all sharp corners. You have created a function. This is the continuous everywhere, differentiable nowhere function, where every single point is a sharp corner somehow. Right? And a sharp corner is weird. Like if you think about a physical object, right? Imagine you're taking the trajectory of a ball as it's thrown in the air. Ball doesn't do a sharp corner. Sharp corner would mean 1 second it's going up at 5 meters per second or whatever, and then instantaneously it's traveling down at 5 meters per second. I've never seen there's some people who are pretty good at manipulating, the Harlem Globetrotters can do their tricks. They can't do that. You can't do an instantaneous change of 10 meters per second in velocity.
Also the ball hitting the ceiling.
Right, sure. The ball hitting the ceiling, right, and you can model it that way. That's not bad. But if you think about if you zoomed in, right, if you got a really fine camera that's doing 1,000 frames per second, you're going to see the ball hit, deform a little bit, slow down, and then do what feels like a pretty continuous transformation there. It's not going to just abruptly change direction, even though, right, at a macro scale, it's going to feel like that, yeah. So mathematicians didn't like this. They were not fans. There's all these great quotes from mathematicians in the day being like, Karl Weierstrass has destroyed my life. They're just really, really upset about this. But it's now, this is one of the early examples of the sort of pathological, sort of what we call fractal behavior. And yeah, we needed to build our mathematical theories to accommodate this. OK, I think this is my last puzzle. Yeah, it is. Number 9. Good. Ready? Cool. Smolian, Raymond Smolian. Raise your hand if you're familiar with Raymond Smolian. OK, wonderful. These great books of logic. You're probably familiar with his style of logic problem. I don't think he invented this, but he's the one who really perfected it. The knights and knaves problem. This guy always lies. This guy always tells the truth. You don't know who's who. What question can you ask? So I think he was probably the closest there's ever been to such a person. He was either always lying or always telling the truth. You got to figure it out. So one thing he would do with his students is he would put 2 coins on the table. So he'd put a quarter here, a penny here. And he would say, OK, here's my promise. You may come up, any student in the class, give me one statement. If it's false, nothing for you. I send you back. If it's true, I choose one of the coins, and I give it to you. So you come up, you say the sky is blue. I give you probably the penny. And then he gets another penny out. You come up and you say 2 + 2 = 5. You get nothing. So the question is, can you say something that will force Smolian, Raymond Smolian, master logician, to give you the quarter? Can you force him to give you the quarter? Take a minute to talk about that with the people next to you. All right. Do we have any candidate statements? Yeah?
You will give me the quarter, or you will give me nothing.
Right. You will give me the quarter, or you will give me nothing. Does that sound good to you guys? Yeah. We can walk through it. Right. You will give me the quarter, you will give me nothing. Can Smolian give you nothing? No, then it would be a true statement. He'd be calling it a lie. Can he give you the penny? No, because then it would be a lie, and he'd be calling it the truth. So he's either giving you either, right? He's only got 3 choices. He's either giving you nothing, he's giving you the penny, or he's giving you the quarter. We've just ruled out nothing would be calling a statement a lie when it's actually true. This would be calling a statement true when it's actually a lie. So the only choice is to give you the quarter. So another way to phrase this is you won't give me the penny, but same idea, right? You'll either give me the nothing or you'll give me the quarter. And so same logic, right? Giving nothing is contradictory. Giving the penny is contradictory, so only the quarter. Anyway, Smolian had been teaching this for a number of years, doing this lesson with his liberal arts students. And then a little while in, 5 years into doing this lesson, he was like, oh, I was more exposed to a certain risk than I had realized. Because someone could have said this. That would have been bad for Smolian, right? To give nothing would be to declare it false. But then it would be true. You're going to give me nothing as one of the possibilities. It would be a true statement. You can't call that false. So you give him the penny. But then you can't do that, because then you're declaring it true, and it's not true. You give him the quarter. Actually, even that's not true anymore, but you're declaring it true. So the only consistent choice is to go take out a loan and try to explain to the bank what happened. Why do you need this money? You're buying a nice, big, fancy home? No, I just got caught in a logical riddle with a student. Now I'm down $1 million. So this is logic, right? The study of reasoning, or as we often experience, the study of being trapped by reasoning. Logic has a way of coercing us. In fact, Smolian uses the phrase coercive logic for situations like this, where just the logic is sort of compelling you into situations you don't want to be in. And of course, logic, right? I'm ending here. In some ways, we should start here with mathematics, because this is what underpins all of it, right? Is applying logical thought to all sorts of structures. And it turns out to be a very powerful way of thinking, even when it fails, I would say, right? So you may be familiar with the sort of grand, end of the 19th, early 20th century project of trying to put all of mathematics on firm logical footing, right? This is something Euclid had done for planar geometry, solid geometry for geometry a long time ago. And it was, okay, can we do this? Can we come up with what is the set of axioms, the simple set of objects we can start with? And then everything in mathematics will be unified. And mathematics can just be boiled down to this process of sorting true statements from false statements. And we'll have something almost mechanistic that can do that. That can just sort true statement, false statement, true statement, false statement. And then, of course, along comes Kurt Gödel. And these self-referential statements are not so fun if you're that way, right? Obviously, Russell's paradox had preceded this. But the statement, I cannot be proven true, is a little vexing. You can't, it turns out in the language that sort of that Gödel develops, it's not, you can't make a statement that says, I am false. But you can make a statement that says, I cannot be proven true. And that turns out to be almost as bad. Because if you prove it true, then it's false. That's bad news. But if you prove it false, then it's like, oh yeah, it definitely can't be proven true. So it is true. And in fact, you've proven it. So that's bad. That's bad. So it can't be proven true. It can't be proven false. Often it's described, these are called undecidable statements. Often they're described as true but unprovably so. Or they cannot be proven true within the logical system you've developed. And this was not great. Nobody really loved this right when it came out, right? Like, and yet, you know, Gödel writes this paper. It was in 1934, Gödel's incompleteness theorems. Alan Turing comes along, reads that stuff really close, develops notions of computability. And like, you know, a few more dominoes fall, and here we are in the 21st century with computers everywhere. And, you know, was Turing's incompleteness theorem like the one pivotal step? Like, no, that's not how history works. Was it a crucial input? Like, yeah, I think so, from what I understand of the history. So seemingly the silliest game that mathematicians play, this like, let's go off and put everything on firm logical foundations. Like, in some sense, who cares? And then in another sense, we all care, because this is the world we live in now. And so there you are. That was all of higher mathematics, 9 puzzles, 1 hour. Oh, cool. Yeah, thank you all for playing along. Nice work with you. You were very efficient in your puzzle solving, so we got through it all. Cool. Questions? Yeah. Right. It's a very natural question. Yeah, I've got to think about it. I haven't done much farming of puzzles for abstract algebra. One situation that I like, Steve Strogatz has written about this. He didn't come up with it. I think it's sort of a classic. Is if you have a mattress on the bed and you want to rotate it, you know, so that it wears down evenly. If you leave your mattress in one position, it kind of wears down. You get the divot where the person's been lying down. So, but the mattress has a nice symmetry group. You can sort of flip it that way, or you can flip it that way, or you can rotate it 180 degrees. And so you can come up with like, what's the right mattress rotation scheme that will make it wear sort of evenly in every direction. I haven't written that up as a puzzle. It's like a cool, I don't know, that might be more of like a chapter more than a puzzle. That's the closest I've got right now. So unfortunately, no. You will notice I covered all of higher mathematics and left out algebra, which is, you know, not a small part of higher mathematics, but, you know, left as an exercise for the listener.
I do have a reminder, if you're asking a question, if you'll come up and use the microphone so anyone who's on the recording can hear the question. Appreciate that.
Cool. Any other questions? Oh, well, I'll be around afterwards too if you want to ask any more in-person kind of question. Yeah? Oh, right, yes.
I was just going to say, continuing off of the question that was just asked, do you have any good set theory puzzles?
Yeah. That's a good question. I got to look through my notes and things. Nothing comes to mind for good set theory puzzles. Although you can just do sort of fun stuff with Venn diagrams. You can make little puzzly situations where it's like, okay, how many in this category, how many in that category. Yeah, what I'm envisioning for this book, it's not actually going to be sort of higher mathematics in a number of puzzles. My plan is Puzzle University is the title I'm working with. And so it's sort of puzzles that touch on all different subjects and branches of what you might study at a university. So set theory, no, yeah, it's funny. Yeah, there's so many good logic puzzles, right? So like, if I were going to look for one, I'd probably poke through Smulyan's books a little bit, because he's got lots of really wonderful logic puzzles. Yeah, but yeah, good set theory puzzle I don't know of off the top of my head.
How about Hilbert's Hotel?
Oh, right. Hilbert's Hotel is lovely. Yeah, right. Yeah, to get into infinite stuff. Yes, Hilbert's Hotel. Yeah, it is one that's almost unsolvable as a puzzle the first time you meet it, because it's just like, oh, I see the answer to this puzzle is a obviously false thing I'm supposed to say. But yeah, Hilbert's, it's great. I mean, it's a lovely like teaching device for that stuff. Yeah, I have a set of puzzles I think probably work better for sort of the math major crowd than for the more general reader I'm aiming at. But imagining different recipes where sort of you have like an infinite cookbook. So imagine kind of a immortal creature that's reading from this cookbook. And it's got things like, okay, you've got, okay, first add a cup of flour, then half a cup of sugar, then a quarter cup of flour, then an eighth of a cup of sugar. And it's like, okay, if the creature wants to save some time and do these steps, not follow all the infinite steps, do it all at once, how much should it add of each, of each ingredient? And then you can do variations on that too, do an alternating series where you're taking out a little bit of sugar. Which is not, vague, reminiscent a little bit of Hilbert's Hotel, not quite the same, right, working with infinite sums instead of countability. No, Hilbert's Hotel does, right, yeah, is right, set theoretic, so not a bad place to look for good set theory puzzles.
Thanks for a great talk. I imagine you have a whole catalog of puzzles that you could have picked from. What's your favorite puzzle that you had to omit because one of these puzzles?
Yeah. I'm always cycling through. So a couple of these are sort of like late insertions. One that I've been thinking about. This is like literally just what I was thinking about yesterday. So I'm not sure this works as a puzzle, but I'll throw it out there. We have a runner named Lazy Jenkins, and coach is like, Lazy Jenkins, you're smart, but you're lazy. You got to run more. I'm gonna make you got to run 10 miles by tomorrow. And Lazy Jenkins is like, oh, I don't want to run 10 miles. So it's okay, I'm gonna give you this pedometer. Pedometer is gonna measure each run exactly that you do. You can break it up. You don't have to do 10 miles all at once. Do 5 miles twice. Do 2 miles 5 times, whatever. It's gonna measure each run exactly, and at the end it rounds it to the nearest mile. And so Lazy Jenkins is like, okay, maybe I can get away with something here. It goes, or maybe no, I don't want to give you that one. I'm gonna give you this other one. This one measures each run to the nearest tenth of a mile. And then it takes those ones that are to the nearest tenth of a mile and adds those up and reports the sum to the nearest tenth of a mile. So if you're Lazy Jenkins, which pedometer do you want? Do you want the one that measures runs precisely and then rounds the total to the nearest mile, or the one that measures each run to the nearest tenth of a mile and then adds up those rounded numbers? Yeah, I see, right. You're advising Lazy Jenkins to take number 2? Yeah, so how far does Lazy Jenkins have to run in that case? Yeah, you get away with like just a hair over half. Because what you do is, this is like a pretty boring way to spend an afternoon, but you run like a 20th of a mile. Okay, now it says I ran a 10th of a mile, stop. Start again, do that again. So you wind up needing to do, 50 runs like this. But each of those 50, is it 50, 100? 100 runs like this. But you wind up only running about 5 miles instead of 10. So that's Lazy Jenkins. Yeah, anyway, so I've got others. Yeah, they tend not to be, right, the higher mathematics is a bit of a big promise, because I tend to steer into puzzles that are less about, sort of require less background. Yeah, although I was enjoying the one you posted today, the bunnies moving around from hole to hole, and right, a couple of us were working on that and trying to think about how it generalizes to larger numbers. I guess we didn't look at the even case, actually. We've got to look at the case we did 5 and 7. We've got to think about 6. Cool. Okay, I feel like it's lunchtime, so I feel like we can go. Anyway, thank you so much for having me at this conference. It's been really fun meeting you all.